Good morning and good afternoon, sixth grade STEM class, and whoever decided to watch this video. And welcome to our small lesson on potential and kinetic energy. Now, you'll notice that the background of this image has to do with, well, drag racing, and that's because this lesson is going to be the launching point for our upcoming Mousetrap race cars. And of course, I'm going to tell you about that in class, but we got to have a little bit of lesson material to go along with it so that we understand what we're working with. Now, I understand this will also be a little bit of review, so it should be a shorter overall lesson. So here we go. All right, so first things first here. Remember that we learned about potential energy, all right? And we learned this in multiple ways, right? From our arms throwing a paper airplane to the chemical reaction when gasoline and oxygen and fire is ready to create an explosion inside of an internal combustion engine. And we learned about potential energy on top of like roller coasters and such. We learned it in so many different ways, right? So in this case, we're going to be looking at potential energy or that stored energy as well, a spring being compressed or wound up, or the potential energy for a rock that's sitting on a cliff, or a book that's sitting on a shelf that, if pushed over, it still has that potential energy, right? Or if the bookshelf were to rot away over time, right? A In a mousetrap, the spring stores the elastic potential energy. It's elastic because it can move back and forth, right? You can also think of elastic energy as to something like a bow being drawn back or a trampoline. When you start bouncing on the trampoline, how it goes up and down and up and down. Or even as you see here, the slingshot, you pull back on it, you create the tension with the rubberized or latex bands, and then you release the stone or the pebble, and that rock continues to go up. Or even in like a wind up toy, you're kind of pulling it back. Or when you were a kid, if you played with those toy cars that you pull back and they move forward. That is all potential energy being translated into stored energy and then being released, right? And of course, kinetic energy is the energy of motion. It can be represented by something that's already moving, like an airplane flying. It has kinetic energy. If the engines were to stop, right, it would still move forward. Remember, an object in motion wants to stay in motion. Or a person cycling, or a car moving in neutral, or a student or skateboarding, or a ball in motion, right? Kinetic energy arises due to the object's motion. You move a hammer down into the nail. The hammer wants to keep moving. The nail doesn't have the resistance to stop that hammer completely, and it keeps driving through that wood, right? So let's see, you got momentum to consider, and then of course the resistance is friction, the wind hitting the airplane, the friction of the axles being well, gravity pulling the person and the weight on the axles as well as the wind. Same thing with the car, okay? And here you got friction of the nail wanting to drive through that wood. That wood is still a softer material than the nail, so the nail wants to push through it, but you have resistance there or friction, right? Um, Kinetic energy depends on mass and speed. You swing a hammer, it has a larger mass, has a larger weight than the nail, and it pushes it forward. You get the idea. So when you're dealing with a say like a sprung weight or a mousetrap race car, all right, you kind of have this sequence happening. All right, so you wind the spring up, okay, in some way, shape, or form. That generates energy input of your energy. You're creating that to happen. Then, if the spring stays compressed, that's potential energy. It's stored until you release it. When you release it, that energy transforms into potential kinetic energy. The lever pulls a spring, or that mousetrap pulls a spring, right? Again, that's kinetic energy and moving parts. The string is attached to an axle, which turns the wheels, right? The wheels turn. Again, kinetic energy. You're now having to overcome motion, right? And then eventually, when the string is done and the energy is already released, that energy is lost by friction, air resistance, and so on and so forth, and the car slows down. Energy is conserved. Remember, we have the law of conservation of energy. Energy can either be created or destroyed. It can only be transformed, right? And then, of course, the total energy in is the energy out plus the energy lost to friction, heat, sound, so on and so forth, right? So as far as your activity today, it's super easy. On Google Classroom, you will find this sheet right here without my face being over there, okay? And all you're to do is to label the image with the following, and I even have lines, right? So let's say that you have clearly a spring here, okay? That spring is what kind of energy? Label it. If you could identify the parts, okay, there you go. All right. So don't forget this bottom question. How might someone increase the potential energy in their mousetrap race car? Think about that. There's going to be multiple different ways to answer that, and provide that for me on your activity. Super simple activity. And of course, hopefully, the next lesson starts dealing with building our mousetrap race cars. I'm looking forward to that.